The next presentation is going to be given by Andrea Michelotti from Politecnico di Torino.
Hello, can you hear me?
Yeah, we can see you. And someone, Tom, can you put up the presentation? Here we are. Okay, the floor is yours, Andrea. Go ahead.
So I can switch the slides just to check. Oh, I can. Oh, yes, some latency, but it's all fine. So I'm really. I want to thank you for letting us present our work, as it has been a huge achievement for us because we are a student team. In particular, I am Andrea Michelotti, head of Aerothermo team from Politecnico di Torino. Our work is titled Implementation of Genetic Algorithms for Supersonic Airfoil Optimization, and these are the team members. Our workflow starts with the optimization algorithms applied to supersonic wings as the hierarchy component of a supersonic vehicle. The objective has always been to get the maximum efficiency at a given lift coefficient. A surrogated model has been created to define the feasible solution space, obtaining optimized airfoil whose performance has been evaluated to understand the algorithm output. Then they have been validated via high-fidelity models, and in the end, future works have been discussed. These are the used programs. The surrogated model implements the shock expansion theory. The problem is constrained concerning 3 design variables because Bezier curves have been used for parameterization of diamond-shaped and 40 elements double circular arc airfoils. An optimization process relying on a genetic algorithm has been run for 3 different Mach numbers, 2.5, 3, and 3.5, and 2 different lift coefficients, 0 and 0.5. The improvements can be seen in the drag coefficient values. The higher the Mach number, the better the results. This is the zero lift coefficient scenario. The maximum thickness point moves toward the trailing edge to reduce the leading edge angle and the consequent shock intensity. In the 0.5 one, the genetic algorithm and hybrid function results differ because the population did not evolve correctly. The optimized diamond-shaped airfoils are almost identical for both scenarios, but the maximum thickness point of the double circular arc airfoil has moved towards the leading edge, resulting in greater lift but higher drag. The validation process relies on C-type meshes with a dynamic refinement function to increase accuracy in delicate parts of the fluid domain. The RAI 2822 transonic airfoil has been validated confronting star CCM Plus and SU2 results. The 3.3% error on the lift coefficient and the 10% error on the drag one can be improved via mesh refinement. The obtained pressure distribution is close to the results of the NASA code, even though all of them show some discrepancies in the shockwave capture. Showing a 3.5 Mach number and 0 lift coefficient optimization result, the diamond-shaped airfoil presents a higher efficiency and a broader angle of attack range than the double circular arc airfoil. In particular, the peak is achieved for a lower angle of attack. On the other hand, the double circular arc airfoil has a wider distribution of maximum efficiency. Anyway, the greatest difference is due to turbulent flow and the consequent boundary layer stability. In the 0.5 lift coefficient scenario, the obtained diamond-shaped airfoil is almost identical to the previous one, while for the double circular arc airfoil, the hybrid function shows better results than the genetic algorithm alone. Confronting different Mach number optimizations, the double circular arc airfoil presents similar results in the zero lift coefficient scenario, while for the 0.5 one, the maximum efficiency is inversely proportional to the Mach number. In the end, the surrogated model has been validated. The broader angle of attack range can be explained considering that in CFD simulations, the results are still plausible even in a detached shockwave scenario. In fact, the surrogated model correctly predicts the detachment. The Onera M6 wing has been validated in view of future works. There are still some discrepancies, but we are confident about future improvements. Thickness constraints and the real gas effects have not been considered. The latter limits the maximum Mach number over the airfoil at 5 or 6. A off-design evaluation, asymmetrical airfoils, and viscous flow will be considered in future works. But in the last weeks, we completed the off-design evaluation. In particular, the double circular arc airfoil has similar behavior for all Mach numbers in a zero lift coefficient scenario. For the 0.51, the airfoil optimized for a 2.5 Mach number is the most versatile in off-design conditions. The higher the optimization Mach number, the narrower the angle of attack range in off-design conditions because of the detached shockwave. All previous considerations can be explained by the theta-beta Mach relation. A thickness-constrained optimization process has been run. Considering a maximum Mach number of 6, a 0.5 lift coefficient cannot be obtained for any Mach number other than 2.5. This is because the flow energy is too high for higher Mach number values. A 0.41 can be obtained up to a 3.5 Mach number for thickness values up to 0.1. For this, reducing the maximum Mach number from 6 to 5, the maximum lift coefficient reachable for a Mach number of 3.5 is 0.3. In a 0.1 thickness constraint optimization process, a Mach 3 scenario shows two completely different results for the genetic algorithm and the hybrid function. The latter has better performance, even though both geometries are still valid. As thickness reduces from 0.1 to 0.08, the efficiency has a 25% improvement, and the angle of attack range becomes wider. The maximum efficiency is higher for lower angles of attack, and the symmetrical double circular arc airfoil has higher efficiency for lift coefficients other than the imposed one, and it is almost constant in all of the off-design conditions, but a 0.4 lift coefficient cannot be reached. For a 0.08 thickness, the airfoil optimized for a zero lift coefficient scenario is a lot more versatile and has higher efficiency than both the one optimized for a 0.4 lift coefficient scenario and the symmetrical one. But for the latter, the value is barely reachable. Looking at the red framed graph and comparing it to the 0.1 thickness scenario, the thinner airfoil has higher performance. For a given lift coefficient, higher values of efficiency can be reached with an optimized airfoil, but the constraining expansion Mach number is reached for lower maximum angle of attack. A non-zero lift coefficient condition leads to lower efficiency compared to a symmetrical double circular arc airfoil, but also this kind of airfoil can barely reach the 0.4 CL value. The higher the thickness, the smaller the performance difference between the symmetrical and an optimizer airfoil. I have some latency, I think. I can ask you for the next slide, please. Thank you. To summarize, SU2 has been used for CFD validation of current optimized profiles using tetrahedral cells and Ibichid flow. Future works will include the viscous flow analysis, further measure refinements coupling SU2 and pointwise, higher order Bezier curves, three-dimensional case studies, morphing, and thermal fluxes in real gas hypothesis. Next slide, please. Thank you. In the end, we can say that the genetic algorithm optimization is fast and valid, especially when coupled with an additional optimization function. The shock expansion theory is a valid surrogated model, even in detached shockwave and high Mach number scenarios. It has been validated using higher fidelity fluid dynamics simulation, and for a Mach number up to 6, a 0.5 lift coefficient cannot be obtained using symmetrical airfoils because the flow energy is too high, but a 0.41 can. A lower thickness results in 25% efficiency improvement, and the symmetrical double circular arc airfoils with a thickness value lower than 0.1 are very versatile as first-try solutions. Next slide, please. Thank you for your attention. We hope you enjoyed our presentation.
First, may I congratulate you for perfect timing. You are the best in the whole conference up till now.
I just
I just wonder talking about genetic optimization, did you happen to compare the effectiveness and the efficiency with the internal adjoint optimization to see how does it fare?
Sadly, for this work, we couldn't add a deeper knowledge on the software, so we use it only for CFD simulations because we had some knowledge about MATLAB optimization algorithms, so we use them for the entire optimization process. But in future works, we hope to continue this work because it began as a one-year work. So we are plenty of improvements.
Okay. Yeah, it will be interesting to see which one fares better.
We will see.
Yeah. Thank you very much. Very interesting talk.